Okay, we're back and we're on to scientific notation. Scientific notation, as I said, can be found in more detail than in the text in Appendix 1A. And it's a sort of a review of what a scientific notation is and how to convert from numbers in scientific notation and and regular what we call decimal numbers. Scientific notation is very useful in science because of the fact that the magnitudes of the kinds of things that we deal with very frequently in science are either very, very large or very, very small compared to everyday items. And scientific notation allows us to express those quantities in ways that are sort of more convenient than the usual kind of number that we would normally use, which again is called the decimal form of a number. Counting individual objects and then writing out a number in the decimal form can get pretty big or pretty small and have a lot of digits when you're representing certain quantities. And being able to change it to scientific notation allows you to sort of recognize the number and to recognize the relative magnitude of the number at a glance. Okay. Um, just an example of why you might want to have something like scientific notation. An example of that would just be trying to count the number of atoms of any given appreciable amount of any one of the chemical elements. Nickels used to be made of actual nickel metal, which is how they got their name. They're not anymore, but they used to be. So assume that you have 12 old nickels in your hand. And so the question we're wondering is how many atoms of nickel are present? Well, the number is actually well, almost ran out of room there. That many atoms. There are 21 zeros after the 2. I counted, so I was counting as I was drawing them. And in order for you to appreciate the magnitude of that number, if I didn't tell you there were 21 zeros at the end, you would have to sit there and count them. There'd really be no other way to do it. And that is a really large number. But as you think about it, 12 nickels is not all that much. You can easily hold 12 nickels in your hand, but that's how many atoms of nickel you have in your hand. And that's because atoms themselves are so small. In scientific notation, you can write that number as 6.02 times 10 to the 23rd power. And again, this number is not so nice itself, but it's a lot nicer than that. And so it's much easier to write this, and it's much easier to understand the magnitude of the number at a glance, instead of having to count all those zeros. Okay, so proper time scientific notation takes a certain form. And that form is a number between 1 and 10. Uh, Actually, it can be equal to 1, but it can't be equal to 10. So it has to be greater than or equal to 1 and less than 10 times 10 raised to a whole number power. And notice this number up here does conform to that. 6.02 is between 1 and 10 to the 23rd is 10 raised to a whole number power. So what that means is you won't have any fractional powers. You can't have like 10 to the 23.5. Okay. This part of the number is called the decimal part of the number. And this part of the number is called the exponential part of the number. Just for terminology's sake, as sometimes we want to use shorthand. And what a positive exponent means is that you write down the number 10 that many times and multiply them together. So 10 to the 1 would be just 10. 10 to the second would be write down 10 twice and multiply them together. 10 times 10, that's 100. 10 to the third would be write down the number 10 three times and multiply them. That's 1,000. 10 to the fourth, write down the number 10 four times and multiply them together. And that's 10,000, and so on and so on. What a negative exponent means is that you write down 1/10 that number of times and multiply. Okay, so 10 to the minus 1 would be equal to 1/10, which is also equal to 0.10. 10 to the minus 2 means write down 1/10 twice and multiply them together. When you do that, you get 1/100th, or 0.01. 10 to the minus 3 means write down 1/10 three times and multiply them together. That gives you 1/1000th, which is 0.001, and so on. And something that's important to remember is, what if the exponent's 0? That means the number is 1. Any number to the 0 power is 1. 10 to the 0 is 1. 10 million to the 0 power is 1. -3 to the 0 power is 1. And what that means is that you can multiply any number you want by 10 to the 0 power and not change its value. And that is convenient for converting from decimal to scientific notation, or scientific to decimal, and as we'll see in a little while. So conversion between decimal and scientific notation can be accomplished in a series of steps. So let's see, first going from decimal to scientific notation. if you got a decimal form of a number, what you need to do is get that number so that it's between 1 and 10, so that it can become the decimal part of the scientific notation representation of the number. So we have to move the decimal point in the number given. So you want the number to be greater than or equal to 1, but less than 10. Then you have to multiply it by 10 raised to the number of spaces that you move the decimal. So if you move the decimal 3 times, that means that you have to use 3 as the exponent. Now, if moving the decimal makes the number smaller, then the exponent would be positive. So essentially what you're starting out with is when you've got a decimal number, and I'll show this in detail in a moment, when you've got a decimal number, you can consider that number to be equal to itself times 10 to the 0 power, because 10 to the 0 is just 1. And so when you're moving the decimal point, you're making the first part of the number smaller, and that means that the exponent has to get bigger starting with a 0. And so counting up from 0 gives you a positive number. And that number will end up being the number of spaces that the decimal space moved. On the other hand, if moving the decimal makes the number bigger, then the exponent should be negative. Because you're starting with basically the number itself times 10 to the 0. And if moving the decimal point makes the first part of the number bigger, then the exponent has to become smaller to compensate. So remember, you're not trying to change the magnitude of the number. You're trying to keep the magnitude of the number the same. You're just trying to change the way that it's represented. So you got to keep things sort of equal overall. So if one part of the number gets smaller, the other part of the number has to get smaller or bigger to compensate, and vice versa. Okay, and this is all to and that's in order to compensate from the changes that are caused by moving the decimal. Because you're not trying to change the value of the overall number. In fact, you want to keep it the same. Some examples here. If you have the number 96,485, now a lot of big numbers like this are often written without a decimal point. That implies that the decimal point comes at the end, so you can draw it in without doing any harm. And if we move the decimal point one place to the left, we get 9,648.5. That's not between 1 and 10. So we can move it again. Nope, nope, aha. 9.6485, that is between 1 and 10. And so that is the first part of our number in scientific notation. The second part is going to be the number of spaces the decimal moved, which is 1, 2, 3, 4. And moving the decimal point made this part, the first part of the number, smaller. 9.6485 is smaller than 96,485. So the decimal point, the exponent is positive. Normally, you don't have to write the plus in front of the exponent, but I just wrote it in to emphasize that fact. If you had a small number like 0.00135, the decimal point is written right here. And in order to get this to be a number between 1 and 10, you have to move the decimal point to the right. And in fact, you have to move it 3 spaces. Because 1.35 is between 1 and 10. So you multiply that by 10 to the third, but moving the decimal point made this part of the number bigger. 1.35 is bigger than 0.00135. So the exponent has to be negative in order to compensate for making the number bigger by moving the decimal. Now, if you're comfortable with it, you can do conversions like this all at once, like I just did, no problem. But if you're just getting used to this sort of thing, then you might want to do it step by step. And I'm just making a note of what I just said a few minutes ago. You can multiply anything by 10 to the 0 power without changing the value, because 10 to the 0 power is 1. Okay, so if you had a number like 1483, 1,483, and you want to change that to scientific notation. First of all, you can take the 1,483 and consider it to be 1483 times 10 to the 0. Because 10 to the 0 is 1, and 1483 times 10 to the 0 is just 1483 times 1, which is 1483. So you haven't changed the value. But what you've done is you've put it in a form that kind of sort of looks like scientific notation. And from there, it's going to be easier to get to actual scientific notation. Now, to get the first part of the number to be between 1 and 10, you're going to have to move the decimal point. We'll try doing that one space at a time. If you move it one space to the left, you get 148.3. That is not between 1 and 10, but it's closer to being between 1 and 10 than 1,483 was. So you're on the right track. We've moved the decimal point in one space in the direction that makes the number smaller. So your exponent on the 10 has to become bigger by 1. So 148.3 times 1 is the same as 1483 times 10 to the 0. And remember, 10 to the 1 power is 10. So what we're saying is 148.3 times 10 is the same as 1483 times 1, which is true. Okay, we can try moving that decimal point one more space. 14.83 is closer to being between 1 and 10, but it's still not there yet. So we're not done, but we're closer. And we moved the decimal point one more space to the left, which made the first part of the number smaller again, which means the exponent has to get bigger again by 1. And so essentially what we're saying is that 14.83 times 100 is the same as these previous two numbers. You can try moving the decimal point again, and you get 1.483. That number is between 1 and 10, So we're done moving the decimal point, but we still have to come up with the exponent. In getting 1.483, we move the decimal point one space to the left again. Moving it to the left makes the first part of the number smaller. 1.483 is smaller than 14.83. So we have to make the exponent bigger to compensate. And that ends up being 3. So 1.483 times 10 to the third is the same thing as 1,483. Now, 1.483 times 10 to the third is the same thing also as 1.483 times 1,000, because 10 to the third is 1,000. And if you multiply that out, you get 1,483. Okay, so far so good. With a smaller number, say 0.0821, you can start out by thinking of this number as 0.0821 times 10 to the 0. Because 10 to the 0 is 1, and so you can multiply the number by 1 and that changes value. Okay. In moving in the direction of getting this number to be between 1 and 10 means moving the decimal point to the right this time. And moving the decimal point one place to the right gives you 0.821, which is not between 1 and 10, but it's closer to being between 1 and 10 than 0.0821 was. So we're on the right track. Anyway, moving the decimal point that one space to the right makes the first part of the number bigger. So now you have to make the exponent smaller by 1. Starting at 0, if the exponent gets smaller by 1, that means it is now negative 1. So in other words, 0.821 times 10 to the minus 1 is the same as 0.0821. If we move that decimal point one more space to the right, we get 8.21. That is between 1 and 10. So we're done moving the decimal point, but we have to come up with the exponent now. Moving the exponent to the right again made the first part of the number bigger. 8.21 is definitely bigger than 0.821. So the exponent has to become smaller again to compensate. So it goes down to minus 2. And 8.21 times 10 to the minus 2 is proper scientific notation, so you're done converting the number. Okay, so that's how you can do it step by step if you're not sure. And it might make sense to do it that way at first until you're comfortable doing it all at once. Going the other way is essentially reversing the process. So what you have to do is move the decimal point the number of spaces indicated by the exponent. If the exponent is positive, you have to move the decimal in the direction making the number bigger. Which means to the right. On the other hand, if the exponent is negative, then you want to move the direction, or move the decimal in the direction making the number smaller. And that is left. Okay, so we can look at an example. Okay, if we have 4.85 times 10 to the fourth, then essentially what we're going to be doing is moving the decimal point four spaces in the direction that makes the number bigger. And any empty spaces can be filled in with zeros. And so we get 48500. So 48,500 is the same as 4.85 times 10 to the fourth. You can also look at it step by step. I'm sorry about that. You can also look at it step by step, and essentially what you're trying to do is change the number step by step until the exponent is 0. And at that point, you can just drop the entire 10 raised to the exponent, because 10 to the 0 is 1. So we have 4.85 times 10 to the fourth. And the first step we will want to do is get it to be something times 10 to the third, because that's the first step in counting down from 4 to 0 for the exponent. Well, if you've gone from an exponent of 4 to an exponent of 3, this exponential part of the number has gotten smaller, which means the first part of the number has to get bigger to compensate. So 4.85 times 10 to the fourth is actually the same thing as 48.5 times 10 to the third. The next step would be to make it something times 10 to the 2. Well, again, the exponent has gone down, so the first part of the number has to get bigger. So it's 485 times 10 to the second. Next step would be make it so that it's something times 10 to the first power. Again, the exponent got smaller, so this part of the number, the first part of the number, has to get bigger. 4,850 times 10 to the first is the same as all of these other numbers. One more step will get it down to being 10 to the 0. Since the exponent got smaller again, the first part of the number has to get bigger. So 48,500 times 10 to the 0, you can drop the 10 to the 0 because it's just 1, and you end up with 48,500, which is what we got up above here. So leads to the same result. Looking at smaller numbers, (3.63 times 10 to the minus 3). Okay, if you've got a negative exponent, you need to move the decimal point in the direction that makes the first part of the number smaller. So that would be 3 spaces to the left. And again, we fill in the empty spaces with zeros, and you end up with 0.00363. And to do that step by step, sorry, still messed up. Okay, step by step. We'll start with the number that we have to begin with. Okay, so we've got 3.63 times 10 to the minus 3. And remember that we want the exponent to end up as 10 to the 0. So that means wherever the exponent starts out, you have to count step by step towards 0. If it's a positive exponent, like up above here, then you have to count down to 0. But if it starts out as a negative number, then you have to count up to 0. So the first step would be going from 10 to the minus 3 to 10 to the minus 2. You have to keep in mind, though, that 10 to the minus 2 is bigger than 10 to the minus 3. So when you do that, the exponent part of the number is getting bigger, which means the first part of the number has to get smaller. So from 3.63, it becomes 0.363. The next step would be make it something times 10 to the minus 1. Again, the exponent's getting bigger, or going up towards 0. So the first part of the number has to get smaller. Oh, sorry. What am I doing? Okay, 0. Now we've got 10 to the 0. Okay, maybe that's big enough. 10 to the 0. Okay, how about that? 10 to the 0. We've reached 10 to the 0 now. That means that the exponent has gotten bigger again. And so we have to make the first part of the number smaller again. So it's 0.00363 times 10 to the 0. 10 to the 0 is just 1, so you can drop it. And 0.00363 is your decimal form of the number. And that is indeed what we got up above when we did it all at once. Okay, so there we go. Okay, there is a little bit in the book on calculations with scientific notation. I'm not really going to do that. You can look that over. It's definitely a good idea to look it over. But I'm not going to do it in detail simply because I'm assuming that anytime you multiply numbers with scientific notation, you're going to be doing it with your calculator. And so going over the rules of how to do it by hand are probably pretty pointless. One thing to remember, though, when doing calculations with scientific notation on a calculator is that when you're dividing by a number in scientific notation, you have to use a parentheses around the whole number in the denominator. That's important because otherwise the calculator will dismiss or will misunderstand what you're trying to do. So say if you're taking 1 divided by 6.02 times 10 to the 23rd. In the calculator, you would take that as 1 divided by parentheses 6.02 times 10 raised to the 23rd power, close parentheses. That's how you have to do it in the calculator. Otherwise, like I said, it's going to misunderstand what you're trying to do, and it'll give you a weird number out. And in fact, I'm going to do it now, just so you can try it and make sure that you can get it. And I get 1.66 and a lot of numbers after that, times 10 to the 24th, or minus 24th. It's also important on these calculators that you always look to see if there's an exponent. The exponents are often hidden way down at the end of a really long number. And so be sure to check for that. So this is to the minus 24 power. If you reported this as just 1.66 and left off the rest of the numbers, that's okay, as long as you get the exponent in there. But if you report it as just 1.66, that's wrong. 1.66 times 10 to the minus 24, that's okay. Okay, the next topic up is reliability of measurements. But I see that I'm almost up to the time limit for this segment, so I'm going to cut it off there, and we'll do that in the next lecture. So I'll see you then.